How small can a programming language get and still be useful? What if we want a programming language that's down to the bare minimum? If you've been programming for a while, but you don't know the concept of a Turing machine or Turing completeness, the answer might surprise you. We really don't need very much to have a full, useful programming language that can solve the kinds of problems that any other programming language can solve. But before we get to the specifics of what we need in a small programming language, let's just think about what a programming language is. A programming language is a way for us to tell a computer what to do. And we can't just use English, because English is a little bit ambiguous. We need something that better maps to the kinds of algorithms that we want computers to be able to implement. So a programming language is a more formal way of telling a computer what to do. Now, computers don't speak our programming languages. Instead, they speak machine code. Code that's so close to the microprocessor that it's not something that a human being would want to write their programs in. So we need a translator. We need a compiler or an interpreter which takes our programming language and converts it into machine code. To get to machine code is a complicated process for a compiler. For an interpreter of a pretty simple programming language, it actually doesn't need to be that complicated. And we'll look really briefly at the end of this at a very, very simple interpreter. So I'm going to tell you now something that might surprise you if you don't have a background in computer science, but you might already be a programmer. It turns out that the kinds of problems that we can solve with one programming language are pretty much the same with other programming languages. That's not to say that all programming languages are the same. Some might have better performance. Some might have better abstractions that make it easier to implement certain problems. Some might have features that prevent errors. Some might have features that make it easier for the programmer to prevent errors. So we might choose one programming language over another for a variety of reasons, including culture and ecosystems, in addition to all the technical reasons that I already mentioned. So I'm not saying that all programming languages are the same. What I am saying is that any programming language that's Turing-complete, and I'm going to explain what that means in a second, is able to solve the same kinds of problems as any other programming language that's Turing-complete. And all the programming languages that you're seeing on this image, like Java and Python and Rust and Swift, they're all Turing-complete. But to explain to you what Turing-complete is, I first need to describe a Turing machine. So a programming language is Turing-complete if it can simulate a Turing machine. What's a Turing machine? It's an abstract model of a machine that can implement any computer algorithm. And Alan Turing, often considered the father of computer science, although there's other folks who were working in the same domain in the same time period, but he's probably the most prominent, came up with the concept of a Turing machine, and therefore Turing-complete is named after him and after that. So to picture a Turing machine, look at this diagram that I have here, and imagine a tape of unlimited length. Now imagine that tape is split into cells that are either blank or maybe they have a character on them. And imagine a head, and it can read or write the character in a cell, including erasing it. So it could go to a cell and say, I'm getting rid of the thing on that cell right now. Now imagine that the head can move left or move right, one cell at a time. Finally, imagine that it can write or move based on the value read. That is, it can branch. It can look at a value and decide, I'm going to go this way because of that value, or I'm going to go that way because of that value. So in other words, the head follows some simple rules, which altogether, when we have all the rules together, can be thought about as a program. And the program might say things like, if this value is read, write this other value. If that value is read, move left one cell. It's just a bunch of simple rules. We're just moving up and down a tape, and we're writing some characters, and we're making some simple decisions based on the characters that we're seeing. There's actually not a lot to it. But that's a Turing machine, and that's actually enough to implement any computer algorithm as we think about computer algorithms today. So what does it take for a programming language to be Turing-complete then, to have this idea of implementing a Turing machine if it had enough time and enough memory, let's say? Well, here's a definition from a textbook. This is from Programming Languages, Principles and Paradigms by Tucker and Noonan. They say, and I'm going to read it, a programming language is said to be Turing-complete if it contains integer variables, values, and operations, and has assignment statements and the control constructs of statement sequencing, conditionals, and branching statements. Notice what you didn't read there. There's a lot in your programming language you didn't read about. You didn't read about object-oriented programming. You didn't read about functional programming. You didn't read about even functions or procedures themselves. You didn't read about a lot of the abstractions that we usually expect in a programming language. And in fact, they continue. All other statement forms, while and for loops, case selections, procedure declarations and calls, and data types, strings, floating point values, are provided in modern languages only to enhance the ease of programming various complex applications. So they're saying all that stuff we don't actually need to be Turing complete. So we don't, to implement computer algorithms, need even floating point values. We could technically do everything with integers. In fact, we don't even need for loops or while loops. We don't need loops at all. We sort of would have them anyway if we're able to jump around from one part to another and have something kind of like if statements, but we don't need those formal ways of writing a loop. So it's interesting because I told you about Java and Python and C++ all being Turing complete, and they have a ton more than what was described as needed by Tucker and Noonan. And all of that is actually just for your convenience. It's not because it's necessary to implement algorithms. So I've simplified this into just a set of bullets. What do we need from their description if we're just thinking about this at a high level? We need integer variables. We need a way to change the values associated with those variables. So that could be something like arithmetic, right? If we have integers, we should be able to add them together, subtract them. That's a way of changing them, and then store those changes back in the variables or the things associated with those variables. We need something kind of like an if statement, right? They said we need control, we need branching. So we need a way of making decisions and then maybe going to another part of the program. If you've ever programmed in BASIC, maybe you've seen go to. If you've programmed in assembly language, maybe you've seen jump. If you've programmed in C, there actually technically is go to as well to labels, but you're not really supposed to use it because it's bad style. But basically it allows us to just suddenly go to another part of the program. So it could say in BASIC, I want to go to this different line number. Or it could say in C, I want to go to this part of the program that has a different label. So if we can jump around the program, and if we can make decisions using if statements, and if we have integers that we can change, that's enough for a programming language to be Turing complete. So thinking about all that and going back to our original premise, what is the smallest possible programming language? It actually can be really small. Enter Brainf, and I'm not going to say it because I don't want YouTube to strike my video. So I'm just going to call it BF. So BF is a programming language that was invented in the early 1990s by a gentleman who was very interested in esoteric programming languages and programming challenges and how small we could make a programming language. It's not a programming language you're going to want to use for day-to-day programming because it doesn't have all those conveniences that Noonan and Tucker were saying are nice to have, but we don't actually need. It has the bare minimum, so it's a minimalist programming language. But BF is in fact Turing complete. And what you're seeing here is actually a BF program that implements Hello World. If you run this in a BF compiler or BF interpreter, it'll print out Hello World. Now, it doesn't look nice again. It's not the way you'd want to write Hello World. It's not pretty like it would look in Python, print Hello World. But not only can Hello World be implemented in BF, any algorithm that you can implement in Python or in Java or in C++ can also be implemented in BF, believe it or not. How does BF work? Well, it has a concept called cells, and you can kind of think of cells like memory or like variables. In the original version of BF, I think there were 30,000 cells. It doesn't really matter how many cells there are, but let's say it's an arbitrarily large number. So we have these cells, and they can hold different integer values. In addition to the cells, we also have the program, the BF program that we're running. And then we have two ways of navigating around the cells and around the program. One is called the cell index, and it just points to which cell we're currently at. And then we have something called the instruction index, and that tells us what part of the program we're currently at. And the different characters in a BF program are able to manipulate the cell index, so change which cell we're at, manipulate the instruction index, so change which instruction we're at, or change one of the values at the cell that the cell index currently points to. So what does the BF language look like? Well, this is the whole language here. It's only 8 characters. There's 8 different characters. There's greater than and less than for moving around the cell index. That's basically going forward a cell, going backward a cell by 1. There's plus and minus. They're for increasing or decreasing the value at a cell by 1. There's dot and comma. This is for input and output, getting a character in, writing it to a cell, or printing a character out to the console. And then we have opening bracket and closing bracket. And this is basically a combination of an if statement and a goto in one. And they only really check against the value 0 or non-zero in a particular cell, but they basically allow loops in a sense. A combination of if and goto, if you think about those two together, they're kind of like a loop. And you can loop between the opening bracket and the closing bracket. So that's not a lot, and believe it or not, to be Turing complete, we don't even need the dot and the comma, because the dot and the comma are for input-output. But if all of our values are actually hard-coded into the program, we don't even need them to have the program. So we actually only need 6 of these characters to be Turing complete. Nonetheless, this is an incredibly simple language. It's a language, though, that can implement any computer algorithm, and so you can write a JSON parser in BF if you wanted to. You can write quicksort in BF if you want to. Any algorithm you can write in BF, just as you can write any algorithm in Python or in C. And BF is a whole programming language. Is it quite the smallest possible programming language? Not quite, but it's really, really close. And implementing it in Python as an interpreter is actually in almost any programming language, is just about 20 lines of code. Here's the main part of a BF interpreter implemented in Python. And if you notice, it's really close to the table we looked at before. We have the variables like the cells, which might be a list or an array of different memory locations. We have the cell index, which we might increment by 1 or decrement by 1. We have the instruction index, which is just continually going to the next instruction, or in the case of where we might hit brackets, maybe jumping to a different part of the program. But there's really not much to it. So here we have Python implementing a whole other programming language in just about 20 lines of code. And of course, there's some support functions that aren't listed here, but it's not much more. The whole thing altogether, an entire BF interpreter in Python, is less than 40 lines of code. I think that's pretty amazing when you think about that BF is Turing complete. So, if you want to find out more about BF and how it's implemented and understand it even better, I just came out with a new book called Computer Science from Scratch. You might have gotten enough in this video, and maybe you don't want to go further. But if you do, and you want to understand more computer science, because maybe you're somebody who already knows, let's say, Python, but you want to understand the layers underneath Python, then Computer Science from Scratch is exactly the book for you. If you're a self-taught programmer, or maybe you're a programmer who has a computer science degree, but you did it years ago and you forgot a lot of the core concepts, then Computer Science from Scratch is going to teach you how programming languages work under the surface. It's going to teach you how microprocessors work. It's going to teach you some interesting algorithms and get you thinking in an algorithmic way. And it's even going to give you a really brief introduction to machine learning. It's a good kind of overview book about the world of computer science for those who know programming but want to understand more about the layers of the software stack that go underneath their programs. So I totally think it's an awesome book because I wrote it. And if you want to check it out, go to computersciencefromscratch.com and you can find out a lot more.